Hello everyone, welcome back to another video. After a lot of requests, finally a convergency video is here. In this video, I'll try and explain the basics of convergency, the use of this concept in real life, and the important questions which may be asked in the exams. So, let's dive into it. Starting with what is convergency? Okay, so as per definition, convergency is the angle of inclination between two meridians over a particular latitude. Let's understand this definition first. So, I have the Earth over here with North Pole and the equator in one frame, as you can see. Now, if I take any two random meridians on this Earth, let's say 30° west and 30° east meridians. From our previous knowledge, we all know what change in longitude is. In this diagram, we can see that the shillong between these two meridians is the angle which is measured over the North Pole, which is this angle over here. Now, this change in longitude is something which remains constant between the two meridians throughout. Wherever I go, the shillong between both of these will remain the same. Let's say I follow these two meridians from the North Pole towards the equator. The shillong will remain the same. Something which does not remain the same and is constantly changing between the two meridians is known as inclination. To understand inclination, let's take the direction of each of these meridians at three different latitudes. I start from the equator and make my way upwards towards the poles. So, talking about the equator, first I'll draw both of those meridians again. Now, if I make a tangent wherever these longitudes are cutting the equator, I will find two lines which will look like this. So for the red meridian, the tangent will be the green line, and for the yellow meridian, the tangent where it cuts the equator will be the blue line. Understood? Now, if I pick the blue line and put it over the green line like this, I see that the angle which the blue line is making with the green line is 0 degrees. So I can say that the angle of inclination between both these meridians at the equator is 0 degrees. Okay, just stick with me, you'll understand this concept in a matter of minutes. Now, this was about the equator. If I move up and I consider a latitude in the northern hemisphere, so first I'll draw both of those longitudes again. Let's say I take this latitude over here, which is 50° north, and I want to find the angle of inclination between the yellow and the red longitudes at 50° north. What I'll do is I'll again make two tangents wherever the meridians are cutting this particular latitude. By drawing tangents, what am I doing? So I'm actually finding the direction of the longitudes at that particular latitude. So starting with the red meridian, the tangent at 50° north will look like this. And for the yellow meridian, the tangent at 50° north will look like this. Now I'll follow the same drill. I'll overlap both of these. So blue over green. What do I see? I see that there is an angle which is formed between the green line and the blue line. And this angle, let's say some angle theta. So this angle theta is my angle of inclination between the two meridians at a particular latitude. So this theta is nothing but my convergency. Understood? So the angle of inclination between any two given meridians along a particular latitude is convergency. That's what we read from the definition. Now, in this diagram only, let's consider what is happening at the pole. So I'll take you to the North Pole now. On the North Pole, I don't have to draw any tangents, or let's say I draw two tangents. So at 90° north, the tangent for the red meridian will look somewhat like this, and the tangent for the yellow meridian will look somewhat like this. Yes, and the angle between both of these will be this angle. Now, what was this angle? If you remember, this angle was nothing but my Shillong, or the change in longitude. So what do I see? So if I draw a table, what I'll see is that at the equator, 0 degrees north, my angle of inclination was 0 degrees. At 50-degree north, it was something, let's say this angle is 30 degrees. And at 90-degree north, it is my Shillong. And what was the value of Shillong? It was 60 degrees. So what I see is that as I'm moving from the equator towards the pole, the value of convergency is increasing. And I can say that this follows a sine function. Now, what is a sine function? So if you remember from high school, the value of sine was 0, 1 by 2, 1 by root 2, root 3 by 2, and 1. And these were for what angles? So for 0 degrees, 30, 45, 60, and 90. A similar thing is happening over here. At 0 degrees, the convergency is 0. 0 degrees what? It is the equator. At 90-degree, convergency is maximum, which is let's say 1. And any latitude between the 0 degree north and the 90-degree north, which is let's say any latitude in the northern hemisphere, the convergency is increasing, or the inclination is increasing. So I can say that convergency is following sine function. And through this, I can find out the formula for convergency. So the formula for convergency is C is equal to Shillong into sine of latitude, because convergency is changing with respect to latitudes, and it is increasing as we are going to a higher latitude. That's why we are following a sine function. Understood? Later you'll realize that this formula will be revised a bit. This latitude will change to mean latitude. You'll see this in a while. So the formula for convergency comes as convergency is equal to Shillong into sine of latitude. Perfect. If you ever get confused between if it was sine or if it was cos, just come back and look at these two diagrams. You'll understand everything. It was 0 at the equator, and as you kept moving towards the north or towards the south, it will increase. And what function increases? A sine function increases. The cos is opposite of it. Cos 0 is 1 and cos 90 is 0. So cos function is reducing, whereas sine function is always increasing. That's why we have this formula for convergency, which is Shillong into sine of latitude. Perfect. Now moving ahead. Another concept of convergency can be explained through a great circle track. Now let's say we are flying this great circle track, which is the red track, from place A to place B. Now let's find the great circle bearing of both the places. So what is a great circle bearing? Great circle I know is the red dotted line. But how do I find the bearing of the great circle at A and at B? So to find any kind of bearing, you need to keep this thing in mind, that the bearing is always measured from the longitude of that place and is measured in the clockwise direction till you hit the particular great circle, or in case of a rhumb line bearing, a rhumb line. So we start from the longitude, continue in the clockwise direction till we hit the great circle to find the great circle bearing. So let me find the two great circle bearings. For that, let me highlight the two longitudes first. So for place A, it is this longitude. Place B, it is this longitude. To find the great circle bearing, I will go to the longitude, continue in the clockwise direction till I hit the great circle. So this is my great circle bearing. Great circle bearing at A. Let's say this angle is 70 degrees. Similarly, to find the great circle bearing at B, I will again go to the head of the longitude, continue in the clockwise direction till I hit the great circle at B. So it is this angle, let's say it is 75 degrees. Okay, now from the previous concept of convergency, if I want to find the convergency between A and B, what will I do? I will take two tangents, compare them, and see what is the angle between the two tangents. So let's do that. For place A, this will be the tangent. For place B, this will be the tangent. So if I take this blue line and put it over the purple line, I see that a small angle is being formed. And this small angle over here is the convergency between A and B. Let's say this angle is 5 degrees. And if you look closely, the great circle bearing at B minus the great circle bearing at A is also 5 degrees. So with this diagram, I can derive another formula for convergency, which becomes convergency is equal to great circle arrival minus great circle departure. So my great circle bearing at the arrival aerodrome minus the great circle bearing at the departure aerodrome will also be equal to convergency. So in this case, it will be 75 minus 70, which is equal to 5 degrees. Now, I told you that there will be a revised formula for convergency as well, in which we will use mean latitude. So that thing comes into play now. If you see place A and B, both of these places are on different latitudes. So how will I put the formula for convergency over here? The previous formula for convergency. The previous formula was convergency is equal to Shillong into sine of latitude. Now, since both the places are at different latitudes, which latitude should I use? So, the latitude which I'll use will be the mean latitude. What is mean latitude? Mean latitude is the latitude which is exactly between the two latitudes. So, one latitude will be approximately this latitude, and for place A will be approximately this latitude. So, the one which I will use will be equidistant from both, approximately this latitude over here. Okay, so in the formula you add mean latitude. So I have two formulas for convergency now. First one is great circle arrival minus great circle departure, and the second one, or the more common one, will be Shillong into sine of mean latitude. Perfect. So let's now talk about Rhumb line and great circle tracks collectively. So we all know how a Rhumb line track looks on the earth, right? It looks like this, which is a curve. Whereas if I talk about a great circle track on the earth, let's say between these two places only, it will be an almost straight line, right? Because it is the shortest distance between both of these places. Now, if I talk about Rhumb line and great circles on a Mercator chart, we can say that on a Mercator chart, Rhumb line is a straight line and great circle appears to be a curved line which is convex to the nearer pole. So if you see, the North Pole is over here, which is the nearer pole, and it is a curve convex to the North Pole. Whereas Rhumb line is a straight line and we have the equator somewhere down below. Okay, so on a Mercator chart, great circle track is convex to the nearer pole, or I can also say great circle is a curve concave to the equator. That is a good way of remembering it, as it makes a cave over here. So if you see, it makes a cave-like structure towards the equator. So great circle concave to the equator, Rhumb line straight line on a Mercator projection. Okay, so let's now move ahead using the same concept which we just discussed. So let's say this is the equator. I have two places, place A and place B. Both are on the same latitude, let's say. Now, if I want to go from A to B, let's find the Rhumb line bearing and the great circle bearing from A to B. So, how will a Rhumb line track look from A to B on a Mercator chart? It will be a straight line, which is, let's say, this line. And the great circle track from A to B will look somewhat like this, considering we are in the northern hemisphere. Talking about the longitudes of these places, the longitudes will look like this, originating from the northern hemisphere for A and like this for place B. Okay, so if I'm told to find the great circle bearing at A or the Rhumb line bearing at A, there are two things which I'll do. First of all, which is the most important one, I will draw the arrows from A to B so that I know my track. So the track is going from A to B. So it will look like this for the great circle and like this for the Rhumb line.
And the other thing is that I'll start from the longitude in the clockwise direction. So if I want to find the great circle bearing from A to B, I will start from the longitude and stop till I hit the great circle track from A to B. So this will be my great circle bearing. Similarly, if I talk about the rhumb line bearing, it will be an angle from the longitude till the rhumb line track. Now, similarly, if I want to find the great circle bearing at B, so great circle bearing at B will be this angle starting from the longitude till I hit the arrow. Understood? Okay, perfect. Now, here, one thing which you need to know is this angle. So, what is this angle? This angle between a great circle track and a rhumb line track is known as conversion angle or CA. Now, what is conversion angle? In this diagram, where can I see my convergency? So, in this diagram, if I continue and make these two meridians go till the North Pole, I'll get this angle. What is this angle? This angle will be change in longitude. And what is convergency at the pole? It is change in longitude into 1. So, this angle is my convergency. Now, the value of conversion angle is half of convergency. So from this diagram, you can see all three things. You can see the bearings, which is the great circle or the rhumb line bearings. You can see the conversion angle, and you can also see the convergency. Similar thing will happen in the southern hemisphere. So if I had two places in the southern hemisphere, let's call them C and D, and I wanted to go from C to point D, I will do the exact same thing. To find the rhumb line track, I will make a straight line between C and D. To find the great circle track, I will draw a great circle from C to D, which will look like this, since it is in the southern hemisphere, always making a cave towards the equator. If I want to draw the meridians will look like this, originating from the south pole for D and like this for C. To find the angles, first thing which I'll do is I will make the arrows from C to D. This will be the arrow for rhumb line. For great circle, these will be the arrows. Now I can easily find the bearing. So great circle bearing will be from the longitude clockwise till I hit the great circle. Rhumb line bearing will be from the longitude till I hit the rhumb line. Similarly, at point D, the great circle bearing will be an angle which looks like this. Okay, so another formula added to the list, conversion angle, which is half of convergency. And what is convergency? Convergency is Shillong into sine of mean latitude. Or it is great circle bearing at arrival minus great circle bearing at departure. So these three formulas are done so far. Now I know you all might be wondering why or what is the use of convergency? Why are we even finding the conversion angle? What will we do with convergency? What is all this? So convergency is a concept which comes handy when I want to plan and fly great circle tracks. So here, if I wanted to go from Moscow to Vancouver, I'll follow the great circle track, correct? This is, let's say, my great circle track from Moscow to Vancouver. Now, this great circle track is a straight line. I know this will give me the shortest distance between the two places. But when I put it on a piece of paper, it comes out to be like this. Now, is it practical for me to fly something which looks like this on paper? No, it is not. But as a pilot, can I carry a globe with a straight line marked on it like this? I cannot do that. I will have to carry something which is a resultant of the Mercator projection, be it a digital chart or a physical map, whatever. So, what I do is I plot the rhumb line track between the two places. So, I will make this rhumb line track between Moscow and Vancouver, and I will find the convergency between the two places. I have the two latitudes and I have the change in longitude. So I will find the convergency. I will find the rhumb line track. And what I'll do is I'll find the great circle track using the conversion angle. So in this diagram only, I'll try and give you an idea. So these are the two longitudes, right? I have a rhumb line track from Moscow to Vancouver. Rhumb line track always measured from the longitude in the clockwise direction. So it will be this. And I have the convergency. From convergency, I will find this angle, which is my conversion angle. And with the conversion angle, I will find my great circle track from Moscow. So this will be my great circle track from Moscow. So I will use this track to fly a great circle from Moscow to Vancouver. And this is how my concept of convergency is being used. This angle will also be conversion angle. In fact, I should write it as CA. It is not convergency, but the conversion angle, which is half of convergency. Okay, so now let's look at the trend of convergency as we travel from east to west and west to east in both the hemispheres. I'll start with the northern hemisphere. I'll take two cases. First one going towards east, second one going towards west, and then I will go to the southern hemisphere. Again, take two cases. First one going to the east, second one going to the west, and later I will compile the trend of great circle bearings. So, great circle bearing is increasing or decreasing from A to B. If I'm going towards west, if I'm going towards east, in the northern hemisphere, in the southern hemisphere, all those things. So starting with the northern hemisphere, I have two places, A and B. I'm in the northern hemisphere. The rhumb line track will be a straight line. Great circle track will be like this, considering it is the northern hemisphere. And the equator is somewhere over here. Okay. Let's start by finding the great circle bearings. So to find the great circle bearing at A, first of all, I need the longitude. Second thing, which is the most important thing I just discussed, is the arrow. So going from A to B, I need these arrows, which are very important. Let's now find the bearings. So first one is the great circle bearing from A to B. Great circle bearing from A to B will be this angle from the longitude till it hits the arrow. Let's say an angle of 80 degrees. Rhumb line bearing at A. So for the rhumb line bearing, again on the longitude till it hits the rhumb line track, which is 90 degrees. Why is it 90 degrees? Because both A and B are on the same parallel of latitude. Now talking about the great circle bearing at B, so starting from the longitude till it hits the green arrow, which will be what? It will be 100 degrees. Now talking about the conversion angle, so conversion angle will be this angle between the great circle and the rhumb line, and this angle is what? 10 degrees. So here, what is the trend of my great circle bearing? So great circle bearing from A to B is increasing. At A, it was 80 degrees. At B, it is 100 degrees. So the great circle bearing is increasing. I will just write an I over here. And I am moving east. Okay, so moving east, great circle bearing is increasing. Now, if I consider the mid longitude, if I take the longitude which is in the middle of A and B, what will be my great circle and rhumb line bearings? So, for the great circle bearing, I will go to the longitude, draw an angle till it hits the great circle, and for the rhumb line, I will do the same thing till it hits the rhumb line. What do you see? You see that this is exactly the same. So at any mid longitude, the rhumb line and the great circle bearings are the same. And in this case, it is 90 degrees. Why? Because the places are on the same latitude. Okay, so this was case one. Now I'll take the second case in which I am moving west in the northern hemisphere. So I have two places, A and B. I'm going from A to B. So the rhumb line track will be like this, and I'm in the northern hemisphere. So the great circle track will look like this from A to B. Before finding the bearings, I need the arrows. So A to B and A to B. Let's draw the longitudes. Longitude of B, longitude of A, and talking about the bearings now. So what will be my great circle bearing when I'm going from A to B at place A? So at A means I will start from the longitude of A. Longitude of A in the clockwise direction till I hit the great circle track. This angle is more than 270. Let's say it is 290 degrees. Okay. Now talking about the rhumb line bearing A to B, it will be this angle over here, which is 270 degrees. Why? Because A and B are on the same parallel of latitude. So with this, I come to know a conversion angle. So the conversion angle in this case is 20 degrees. Okay, so what will be my great circle bearing at B? To find the great circle bearing at B, I will go to B, start from its longitude, continue till I hit the head of the arrow, which is over here.
How much will this angle be? Great circle bearing at departure is 290. Conversion angle is 20 degrees. Convergency will be 40 degrees, and great circle arrival minus great circle departure is 40 degrees, which is convergency. So my great circle arrival will be 250 degrees. So what do I see over here? I see that my great circle bearing from A to B is decreasing. So in the northern hemisphere, moving west, great circle bearing decreases. Let's talk about the southern hemisphere now. So I'll again take two different cases, starting with moving east. I have two places, A and B, and I'm going from A to B. So what will my rhumb line track look like? So the rhumb line track from A to B will be a straight line, arrow from A to B. And how will the great circle look like? So the great circle track from A to B will be in this direction this time. Why? Because I'm talking about the southern hemisphere. So for your reference, I'll draw the equator also. So this is the equator over here. Above the equator is the northern hemisphere, below the equator is the southern hemisphere. Let's talk about the different bearings in this diagram. For the bearings, I know that I need to know the longitudes. So longitude A, longitude B. In these four diagrams, I'm taking longitudes to be straight lines just for the ease of understanding. Otherwise, we all know that longitudes are also curves, like I used in the previous diagram. Okay, so I have the two longitudes. I missed one of the arrows. So A to B, these two arrows for the great circle. These arrows are very important. You'll realize this when you're solving the questions. So never miss the arrows, because if you have the arrows and if you have the longitudes, all your answers will be correct. Let's find the great circle bearing at A. So it will be this angle from the longitude till it hits the great circle. Let's say this angle is 120 degrees. Rhumb line bearing at A, starting from the longitude till the rhumb line, which is 90 degrees. So my conversion angle comes out to be 30 degrees. Now, since the conversion angle is 30 degrees, what will be the great circle bearing at B? To find that, again go to the longitude, clockwise direction till it hits the arrow. So this angle will be 120 minus convergency. So this angle comes out to be 60 degrees. So here again, what I see is that my great circle bearing is decreasing. So I'll write another D over here. So moving east in the southern hemisphere, great circle bearing decreases. So now the last case, moving west in the southern hemisphere. So two places, A and B. I'm going from A to B. So rhumb line track will be a straight line with the arrow over here. How will the great circle look like? Great circle from A to B will look somewhat like this. Arrows from A to B, talking about the longitudes. So longitude of B, longitude of A. Now I have everything in the diagram. Let's find the bearings. So great circle bearing at A from the longitude clockwise direction till it hits the great circle arrow. Let's say this angle is 200 degrees, more than 180. And rhumb line bearing A to B will be starting from the longitude till it hits the rhumb line, which is 270 degrees. So what is my conversion angle? I have a conversion angle of 70 degrees in this case. 270 minus 200. Now talking about the great circle bearing at B. So I'll start from the longitude in the clockwise direction till I hit the great circle, which is crossing B. And I see that this angle comes out to be 340 degrees. So I can say that the great circle bearing in the southern hemisphere when I'm moving in the west direction is increasing. So I have all four diagrams ready. Moving east in the northern hemisphere, moving west in the northern hemisphere, moving east in the southern hemisphere, and finally moving west in the southern hemisphere. So I can make this table. So in the northern hemisphere, when we were moving east, it was increasing. When we were moving west, it was decreasing. In the southern hemisphere, when we were moving east, the great circle bearing was decreasing. And when we were moving west in the southern hemisphere, the great circle bearing was increasing. So IDDI. And we also saw that the difference in great circle bearings at departure and destination is my convergency, and half of it is my conversion angle.
Okay, so that was all about the theory part of convergency. Since this has been a long video so far, I'll make another one in which I will take up some important questions which you must be able to solve for your navigation exam. I hope you understood this topic of convergency well. Feel free to hit me up in case you have any kind of doubts from this topic so far. Also, please let me know via email if anyone's looking for online navigation classes. I'll see you next time, and thanks for watching.